Let's talk about Faraday's law and Lenz's law. In the previous video, you should have seen a number of demonstrations of both of these laws, but I thought I'd throw in another one. I have here a powerful magnet. I don't know how many Teslas, but it's probably at least a third of a Tesla at the end of this plastic rod. I have here a solenoid, which is basically a number of wires wrapped around a core. In this case, the core is plastic. And two diodes. These diodes are wired so that they only one of them will light up if the current is in a certain direction. If the current is in the forward direction, let's say, this one lights up. If it's in the reverse direction, this one lights up. So Faraday's law is a law that says that the induced EMF around a loop bounding a surface, so the surface is this hole, and the boundary of that hole is all this coil. In fact, each coil is separately affected by Faraday's law, and then when you sum it over the entire solenoid, you get the total effect. So what it says is it's equal to negative, I'll explain that negative in a moment, times the rate of change of magnetic flux. The magnetic flux is a quantity that combines the effect of the magnetic field and the area over which it acts. I'll give you a more precise definition of flux, but basically it can be thought of as a product of the magnetic field and the perpendicular area. So once you have that, the rate of change of that flux, if I just keep the magnet there, nothing happens. But if I change it, that's when you'll get some effect. So let's try to change it. I'll withdraw it because withdrawing is easier in this case. You'll notice that withdrawing makes that LED light up. Inserting will make this LED light up. Half the time I'm hitting the thing, so this one is going to be a bit hard to show, but it's right there. So this effect is real, and in fact it's responsible for all the electricity that you consume. Now the minus sign is an interesting thing. This law is so important that the minus sign itself has got a name. It's called Lenz's law. And the way the minus sign comes about is rather interesting. So what Faraday's law says is that I'll draw this coil a little bit thick if it's coming toward me. So let's say you have a coil here, okay, and you have a magnet with its north pole coming in. So what Faraday's law is going to tell you is that the system is going to behave so that the induced EMF will be negative of the rate of change of flux. Now the magnetic flux coming in from a north pole spews out something like the positive charge type magnetic field. Okay, so in an electric situation, that would be a plus charge, and electric field would come out like that. In the same way, a north pole would send out these magnetic field like that, which means that into this coil there's currently going to be magnetic field that's into the page, into that coil as we are seeing it, with this thick portion of the coil towards me. So that's how it looks. Now as I bring this coil closer, the number of X's will increase. So the rate of change of X is increasing. That negative sign means that the coil is going to behave in such a way that that increase is opposed. So what the coil is going to do is the coil is going to send out current in this case, so that magnetic field of the opposite type is created. The opposite of X is dot. Dot means magnetic field is coming out of this side. So in response to the increased magnetic field coming in, piercing through the area of this loop, or the surface of this loop, due to the north pole coming towards it with some speed v, the loop is going to fight back and try to create an induced current, actually an induced EMF, but in this case it'll be translated into a current because it's a conducting coil. So how is that done though? Using the right hand rule, we'll know that a current of a magnetic field of this type is only produced if you have, by the thumb rule, current flowing in this direction, which means the induced current is going to be flowing, I prime is going to be flowing like this, or in this case it flows such that it flows towards the bottom on the side closer to me and top on the side away from me. So that's how Lenz's law works. And what this does is, this behaves as another north pole, because remember, the magnetic field coming out of the coil means the coil is now behaving like a north pole, and that north pole fights this north pole and makes you struggle to bring it closer. And that makes sense, because if the opposite were true, if I did not have this negative sign, then imagine what this would mean. It would mean that I start out a north pole moving a little bit, that does not happen, then that means the north pole will get sucked in. That violates energy conservation. Not having the negative sign violates negative conservation, energy conservation, and that's what Lenz realized, and he quickly put the negative sign there in Faraday's law. Faraday did not initially have it. So that's why the negative sign is an important thing, and it's given its own name, namely Lenz's law. And by the way, this resistance that you feel to something is not easily discernible when you're trying to push a magnet through a coil because you're so strong, but it's clearly seen in the previous demonstration, video 9E, when I turn the crank of a generator. If you turn the crank of a generator without any bulb being screwed in, it's very easy to turn the crank. But the moment you screw the bulb in, it's hard to turn the crank, and that's a feature of Lenz's law. Okay, so this is Faraday's law. How to use it? It's a complicated looking law. As you can see, this partial derivative, and that's an open flux. The reason there's open flux is because Gauss's B law makes closed fluxes useless. So we have to only deal with open flux. So let's take a simple example. Here's a one-turn coil. If there are n turns, we'll just multiply everything by n. So it's a one-turn coil, and there's some magnetic field piercing it. Okay, some magnetic field B. And let's just for the moment imagine that it's constant throughout this, okay, in both magnitude and direction. And soon we'll change that. Now there's going to be a unit vector. If this loop is planar, that is, there's going to be a vector n hat, and that's going to be the area vector of this loop. Okay, so we're going to think of that as an area vector and use a right hand rule of this type. So if this is some imaginary direction of travel, then that will be the loop direction. So the area vector will make certain angle with the B vector, let's call that theta. The open flux, phi B open, is just the double integral over the surface S of B dotted with the area vector, dA. The area being, for each little element, you take the area vector and then you integrate over the whole thing. That's B dot dA. If this loop is planar, and if it is a constant magnetic field making a constant angle with every single dA vector in the loop, this can be simplified into just B times A times cosine theta, and that result is only valid for planar loops and constant B. But that's an important case, and if there are n loops, you just put an n there, and then you have NBA cosine theta, our favorite flux expression. So I'll write that too. Now, in general, though, it can be very complicated, but for this particular video, I'm going to stick with NBA cosine theta as being my favorite way of measuring flux. So I know the right-hand side somewhat, at least for a planar coil. And most coils and applications are really planar. What about the left-hand side? The left-hand side stands for the EMF. EMF is like the purest form of voltage without any resistance. Now, by the way, Faraday's law says that the EMF is generated no matter what. So if I take this piece of wood and I put a magnet through it or near it, according to Faraday's law, there's an induced EMF across any curve C which bounds any surface on this piece of wood. That wood got a little charred because I burned something. But what that really means is the induced EMF is a pure form of voltage. It doesn't really need to exist. A voltage cannot be measured across wood. But if you have a wire, then that voltage can be captured and becomes a current. Okay, so this has to be a very abstract statement. So once you have this, I can write E equals negative d by dt Now the partial derivative I'm going to remove, because in this case things are changing in a very definite way. The partial derivative will come back when we're talking about waves, and there you'll need the partial derivative because things are moving both in space and time. Okay, mostly coils are either moving in space or in time, so we'll remove the partial derivative for now. Now you see that d by dt can, number of things can change. The number of turns can change. Well, that would be a pretty bad situation where the coil is unraveling, so we won't consider that. The magnetic field can change. Well, that's certainly possible. You can be moving away from the Earth or be moving towards a neutron star. The area can change. You can be squishing the loop or changing the shape of the loop, or the loop itself can be turning. If the loop is turning, it presents a different area each time, which can be either captured by the area changing or by the theta changing. Usually it's easier to capture turning of a loop through theta changing. So you have three of those cases, and all three of those cases are dealt with in the notes in great detail. Let me just focus on the most important application, which is a generator. So in a generator, you're turning a crank. Okay, so theta is going to be some initial angle theta naught plus omega naught times t, where omega is the angular frequency of cranking. So omega naught is constant cranking frequency. Angular frequency. Now the reason it's constant cranking, if you have played with one of those crank radios or crank flashlights, you'll notice that if you don't have a constant angular frequency, the flashlight will go on and off in a very erratic fashion. So constant cranking is important for a good steady EMF. And of course, if you have something like a waterfall or nuclear power, that first burns water into steam, and then the steam then goes and powers the turbines. That's all a very nice steady situation, and it will lead to a constant cranking. Constant cranking is almost always achieved in real life. So let's just take that constant cranking case. Now N is not changing, B is not changing. Let's say you have a powerful electromagnet that creates a generator, and then the area is not changing, the coil is pretty intact. Only thing is that's changing is theta. So what I'm going to do is I'm going to pull everything out except theta. So I get minus NBA d by dt of cosine of theta naught plus omega naught t. Well, that's an easy thing to differentiate. The derivative of cosine is minus sine. That minus will cancel this minus, and I'll get NBA. But notice, by the chain rule, I have to go inside, and I'll pick up a omega naught sine theta naught plus omega naught t. This is the famous generator equation. The theta naught usually is considered to be 0. So this part, sine omega t, is what gives you the AC current, AC voltage. So that's why all our voltage that we use in daily life is AC, because this is what comes out of the generator. For this to become DC, you'll have to pass it through what's called a rectifier, and that spoils some of the characteristic of the EMF. That's why you get the pure voltage. The voltage that comes out of a place like Niagara Falls, Penstocks, it's going to be very high voltage. So what they first do is they step it down, and those I think 5 to 10 kilovolt transformers are located on poles throughout. So next time you go driving out, look at those poles, and you'll find little cylinders, shiny cylinders sometimes attached to the poles. Whether you live in rural areas or urban areas, you'll find these shiny cylinders. They are usually 5 kilovolt to 10 kilovolt transformers that step down the high voltage wires that are coming in to your house, and then these will then go to your house. Okay, so that's how it's done. And the number of turns obviously increases the EMF. The magnetic field has to be pretty big, and the area of the coil can be made pretty big. So all these things are under your control. The cranking rate is under the control of nature. If the waterfall is behaving well, you'll get a good cranking rate. So that's how the most famous application of Faraday's law is this. Now the EMF does not automatically lead to current. Current comes when you have the EMF and divided by some resistance. That's when you have the current flowing. But this EMF exists whether or not you have a actual resistance to convert it to a current. And that's one of the important things about this business.